Good morning. My name is Philip Kufeldt, and I am a technologist inside Seagate's Research and Development Group. Today, my talk is going to be on the application of computational storage. It's a primary focus of my research, and I'm going to be focused on Ceph during this talk. Let me give you a little bit of background. I've been building computational storage devices since 2015. Back then we chose to use key value as the initial fixed function in these devices, namely kinetic. So we called them kinetic drives, but they were functionally computational storage devices that did key value as a fixed function. While I was at Toshiba, the kinetic drive we demonstrated also did a programmable function as well. We embedded Ceph inside the device. But the problem wasn't creating the devices and the software. The problem was showing the value to existing systems. We had this nice new device, but no software, no mainline software used the kinetic protocol. So showing the value was very difficult without a fairly big, sizable integration effort. So consequently, kinetic kind of faded off into the background, but Seagate has continued to do research with kinetic and has continued to improve and utilize kinetic in our research group. My research is focused on exactly that question. I want to be able to essentially ask a testable assertion of, is an offloaded version of an existing software platform better than the baseline? For my research, I'm targeting Ceph, and I'm specifically examining whether or not offloading key value, because Ceph uses key value extensively inside the OSD. Both BlueStore uses key values for both metadata and data. And if we offload those, is there a benefit? Examining programmable function offload as well as part of my research. A little bit of background here. I think we've seen these pictures before in the past. This is a Ceph architectural overview. Ceph is a collection of OSD servers that essentially manage the disk drives and provide I/O operations to those drives. There's a series of monitors that maintain membership of the cluster. Above is a client tier that uses various interfaces into Ceph, such as a block or a file or S3 interface. All of those interfaces are implemented using Rados, which is an underlying object API. Some of the problems that we're focusing on this research is that a fixed server ratio, that once I define an OSD server, the number of OSDs that it manages remains the same unless there's been drive failures, but I can never expand it. I can only reduce it. And finally, the blast radius, that if I lose an OSD server, I lose all of the media that's attached to it, which can be terabytes in terms of hard drives. That means that all that needs to be re-replicated or re-erasure coded when it's complete, when that failure is recovered. My research is kind of broken up into two phases. I'm going to look at essentially offloading key value first, which has the added benefit of disaggregating the drives. So how am I going to do that? I'm first going to essentially containerize the OSDs, which has already been done. It's available on the network, and I will just leverage that. But then replacing the direct attached storage with computational storage service key value drives, which are essentially network accessible. This allows the OSDs to be scheduled anywhere inside the cluster because they access their local storage via a network protocol and not a SATA or NVMe link. This means that we get to get rid of the entire OSD tier of servers. That means that I have a flexible server storage ratio. It's really a question of how many OSDs do I schedule on a container server, and I can change that dynamically. Blast radius is reduced down to a single drive because if a container server goes down, I just reschedule those containers on other servers. Phase two is where we take those containers and we basically move them back to the drives themselves. And now we have OSD drives completely encapsulating Ceph inside the drive itself, which allows the sellable cycles in the container servers to be reused and used for other purposes. But we're not going to focus on phase two in this talk. We're going to focus on phase one, and that work is ongoing, and we're going to talk about that now. to essentially integrate in a key value network drive into Ceph, I'm going to have to modify the object storage daemon itself. This is kind of a high-level block diagram of some of the code that's inside an OSD. You know, you have the Rados API layers on top, which accept the I/O requests from their clients, and also interact with other OSDs inside the cluster. There's the object methods. These are the extensional object classes that Skyhook uses to define new functionality as part of the access methods. That's all done at that level. There's durability. This is where replication, erasure coding via OSD to OSD operations. But in the back end is the actual object store itself. This is the unit of code that manages the drive and knows how to essentially break up objects, store them on the drive, and retrieve them from the drive as requested. The object store itself is really a class that you can implement different providers of the object store. And right now the choices are Blue Store, which is the default. This is what everybody uses today. In the past, it was File Store. That was the legacy object store that was built on top of file system technology. There's also Mem Store, which is really more of a performance tool. It's a non-volatile object store, or it's a volatile object store, excuse me. K-Store, which is an experimental one that uses key value to store and retrieve its data. So that's what we're focusing on this research, is that we're essentially using the K-Store implementation. And inside K-Store, they implement another object class called Key Value DB, which abstracts the K-Store away from individual key value database implementations. With this class, I can essentially bring up a K-Store on top of RocksDB, LevelDB, Memcache, or Kinetic. So again, in this resource, I'm focusing in on utilizing the Kinetic store. This code is all available as experimental features. Some of this code is no longer available in the latest releases. It's been cleaned up because the Kinetic code hasn't been used in so long, but it's still available in the Nautilus release, and that's what I'm using for my research. I have brought up all of this code, and I actually have Ceph OSDs that are running on top of Kinetic right now, and I'm beginning to do the performance analysis and have already found issues that I'm resolving. Let's do a quick Kinetic Key Value refresher. It's an authenticated TCP/IP protocol. It can use SSL or not. It has end-to-end checksums to provide data integrity. It has ACL-controlled accesses, allows you to segregate the key space and permit controlled access to various parts of the key space. It has sync and async APIs, and it has cache control that allows write through, write back operations, as well as being able to flush and control the cache. It implements an in-order key value database, specifically as a log structured merge tree, which provides basic key value operations such as get, put, and delete. Because it's an in-order key value database, it also has range operations that allow you to do get next. So I can iterate through keys by just getting the next key or getting the previous key. I can also get the list of keys in a key range by issuing a get range call. It has transactional operations as well, compare and swap via put that allows you to do an atomic guaranteed atomic put as long as that data hasn't changed since the last time you looked at it. It also has a compare and delete via delete as well. It has a batch operations that allow you to group up puts and deletes into a batch, and either all of the operations complete or none of them do. It has peer-to-peer operations that allow you to do kinetic drive to kinetic drive operations. So I can say, put this drive locally, but also put it on this drive and this drive as a single command to a kinetic drive. And of course, it has various media and security management operations. One of the things we found initially as we got the Ceph cluster up and running, we saw big performance problems. We started to do the analysis, and immediately one of the biggest offenders was our own, Seagate's own Kinetic client. And we were using the C++ client, and it had some pretty significant problems that we felt like the only way to remedy was to rewrite the library. And we felt also that this would provide us a nice performant backend that we could then port to Python, Java, and a bunch of other places to provide differing language bindings. It's broken up as a research tool to allow us to test against various different protocol versions of the Kinetic protocol. It also has differing backends, because one of the things that's changed over the last 5 years is that the access APIs to the network stack has changed over the last 5 years. We have legacy kernel sockets, but we also now have DPTK, some zero copy things in the form of kernel splice. We have IOU ring. We have smart NICs, and we even have new protocols such as Quick. So we felt like if we put some flexibility in the back end of this library, it would allow us as a research tool to test the various different backends to see, what better performance we get from the differing backends. This was brought up this summer, and we're in the process of testing it right now. One of the things that we noticed as we were doing that Kinetic library is that it would be fairly easy to add a exec call for programmable functions, which I think is a necessary piece for computational storage, is to allow general purpose functions to be inserted in the drive and exec inside the drive. How this would work is that you would essentially build your function into a shared object, and then store that shared object into a key value pair on the drive itself. And then there would be an exec call that would be added to the protocol that would accept a function key, and then either a key range or a key list as operands to that function, and possibly some random parameters that the function can define itself for its operation. Once that exec call comes in, it would access the objects locally, run the function against those objects, and generate a result key value pair that would be returned as a part of the result. But it also would be left around so that you could do a get on that key later on if you wanted to return to the results of that operation. We're initially going to implement this with the user Berkeley packet filter, and we are looking to Skyhook for input, because we see this as an interesting feature to take some of that arrow functionality and push it down to the drive and have it run locally. Performance testing. We need a tool to do performance testing because we need to be able to test our different Kinetic libraries and prove that we did a good job. We also need to diagnose server performance issues, which means running a benchmark on the drive without the network there to isolate the actual Kinetic server. So we need a lightweight tool. YCSB is sort of the tool of choice, but it's very heavy. It usually sits on top of large software stacks, and consequently, it being heavy really isn't noticed. But it's Java-based. Test case definition requires Java programming, so it really doesn't fit for our needs to run in a restricted environment. RocksDB is tied to the Rocks API. It's not interesting. Samsung hit the same problem, implemented KV Bench. It definitely has more flexibility in defining test cases, but it's still limited. It also is tied to the SNIA object API, which is another layer to go through, which we'd have to port to our drive. So I've opted to look at FIO and implementing an FIO engine that essentially utilizes the standard read-write and test case methodology, mapping that to get, put, and delete. I'm doing some tricks with using the offset to define a key. That trick requires us to load the key value data set before running the benchmark, which is very common in key value. YCSB has to do the same thing. And we're also providing with the FIO the variable key size to test 16 byte keys versus 128 byte keys, for example. But the basic code is done. I'm debugging it now, and I might extend FIO for better KV testing. What does the hardware look like? I only have a few more minutes left. It's essentially the hardware we're using right now is what we call an interposer card. It's a small PCB that slides onto the front of a hard drive. So it connects via SATA to a hard drive, but then on the other side of the card, it's providing dual 2.5 gigabit Ethernet. Via the connector. It has an SoC, DDR, and network support on the card. And it plugs into a 4U enclosure that has 96 drive slots. Each of the drive slots are compliant to SFF 8639 and 9639. They support 2.5 gigabit to each slot, so they're dual redundant Ethernets to every slot. And it has redundant 240 gigabit per second uplinks to the top of rack switch. So this provides us with the hardware we need to do the testing. And then with that hardware, we have implemented Ceph clusters that allow us to do comparative testing. Of course, we'll use FIO on the drive itself to make sure that the libraries and the server that's inside the HDD are performant. But when we comes to comparing it for the ultimate goal of comparing baseline Ceph with offloaded Ceph, we need to do this in a Ceph environment. So basically created a cluster that allows us to define different OSDs with different object stores. So we have a blue store, a K store with RocksDB, and a K store with Kinetic. And then we've implemented RBDs on top of that, and allows us to do RBD testing that go through each of the individual paths independently. And we've done that through various crush rules and pools. Final thing is I want to thank Aldrin Montana. He was my intern this summer, and we were able to get the Kinetic C library written this summer. He was fantastic, and I really appreciated all his help. And he's going to continue to work with me in the fall. So I'm really looking forward to the rest of the fall with him. That's it for my talk. If you have any questions, let me know. You can always contact me, and we can talk about this offline as well. Thank you.